Today we're going to look at review questions derived from the review document that's available in Brightspace and in person. And I've highlighted some of the ones that I want to be sure and cover. And we're going to, that's it. We're going to take them one at a time. If they're highlighted, I'm going to review them. For Chapter 8, this is material to be covered in Exam 3. All right. So let's get started with number 1. Number of grams and 2.58 moles of sodium carbonate. All right. As always, when you're solving a problem, it doesn't have to be chemistry. It could be physics, math, any type of problem. First thing you ask yourself is, what's the question? What needs to be answered? And in this case, the question is the number of grams. So we know we have to end up with an answer down there with the number of grams. Now, how do we get there? Right? Our starting point is 2.58 moles of sodium carbonate. Okay? 2.58 moles of sodium carbonate. How do you get there? How do you go from here to there? This is one of those cases of dimensional analysis, conversion factors that tend to solve a very large number of problems in chemistry if you just work the units of measure. We need to go from moles to grams. Do we have a conversion factor that will go from moles to grams? And the answer to that is yes. All right. Moles needs to be on the bottom to cancel these moles, and then grams on the top because that's where we're headed. All right. How do we get grams per mole? What is that? It's molar mass. And to get molar mass, you have to know the formula. You have to either be given the value or you have to know the formula for the compound that you're assessing. And in this case, it's sodium carbonate. All right. So early on, when I said you need to learn how to name compounds, this is one of the reasons why. Sodium carbonate, we know it has sodium, right? Carbonate's not an element, it's a polyatomic ion. And you look that up in the chart that I gave you. Right? So this is a metal and something in the non-metal position. Sodium always has a +1 charge. How about carbonate? Carbonate is a 2- charge. Right? That's fixed. It's in the table. So we know that we need 2 of these to balance those 2 minuses. So there's your formula, sodium carbonate. Now you need to assess the molar mass of sodium carbonate because that's what we need for that conversion factor. All right, sodium, we need 2 times 23, I think. Yeah, 23 for sodium. And 1 times, well, we better do, carbon is 12.01. There's only 1 of them, but there are 3. There are 3 oxygens, and each one of these is grams per mole. So we can add them all together. And this is where you get your calculator out. Let's see, that's 46 and 12.01 and then 48. So this is 106.01 grams per mole. There you go. Now you have your conversion factor. The thinking part, it's all done. The rest is just number crunching. We take this value times that value, 2.58 And we get, our calculator says 2.735058 times 10 squared. Okay. How many significant figures can we keep? 3. So we have to round to this position. That means 274 times 10 squared. Now you look at your answers. What format are they? Format is standard notation. So we have to change this, move this 2 to the right, 274. And this is 274 grams. That's a dimensional analysis problem. All right. Number 2. 8.52 grams of water contains how many molecules of water? What's the question? Molecules of water. We want to end up down here with molecules of water. Okay. Where's our starting point? 8.52 grams. Grams of water. Okay. Do we have a single conversion factor that will go from grams of water to molecules of water? And the short answer is no, we don't. But we do have 2 conversion factors that can be chained together and give us our answer. First of all, we have to change mass to numbers. And the ratio there is the molar mass. Like that. Now we've calculated the molar mass of water numerous times. So I'm not going to do that one the hard way. I'm just going to put the value in there. All right. That goes from mass to numbers in moles. Now we can convert from moles to molecules. And our conversion factor now is 6.022 times 10 to the 23rd molecules. Avogadro's number. I suggest you memorize that one. Okay, now the thinking's done. The rest is, as the saying goes, number crunching. 18.02 divided into it. That gets rid of these. Now we want to get rid of those. And my calculator says 2.84725 times 10 to the 23rd molecules. Okay. These are exact numbers, right? They have no limitations from these numbers on the outcome. This has 3 significant figures. We can round that one to 3. 2.85 times 10 to the 23rd molecules. Okay. All right. I think the first group is in numerical order, so we'll move on to number 3. All right. Now, actually, number 3 is an easier problem than number 1 because you're given the formula for aluminum oxide. The question is, how many moles? And the starting point is 78.8 grams. All right. So that was fairly straightforward. This is a single step problem. We just need to know the molar mass of aluminum oxide. Right. So 2 aluminums is 2698. There. And 3 oxygen, excuse me. and 48. This is 101.96 grams per mole. And we need grams on the bottom, simply because this is in the numerator, that has to be in the denominator to cancel the unit we don't want and leave us with the answer we do want. All right. So I'll take that and divide it into 78.8. And I get 0.77285. We can keep three significant figures. So we round to that position, 0.773 moles. Okay. That's number 3. Now we're going to change gears, shift gears a little bit with number 4. Which of the following compounds has the greatest percent by mass of oxygen? Percent by mass. Here we have 5 named compounds. And if we're going to calculate percent by mass, we have to know the formulas. So I'm going to set this up as an assembly line, Henry Ford time. You know, A, B, C, D, and E. The first one is potassium carbonate. We know it has potassium. We know it has carbonate. Potassium is an alkali metal with a +1 charge. This is a 2- charge, so we have a 2 there. We're going to do the formulas first. Nitric acid. Ics come from ides. So nitric acid would be, actually it's 8. Nitric is from 8, nitrate. So we have NO3 and then 1, because this is a -1 charge, that's a plus. So there's our formula for nitric acid. And zinc 2 oxide. It tells us the charge is 2+ for zinc. And we know oxygen being a chalcogen is 2-. So that's the formula, right? Already balanced. Sulfur dioxide. Okay. And diphosphorus pentoxide. Diphosphorus pentoxide. You need to know your Greek prefixes, right? All right, so let's remove the charges so they just don't muddy the waters. Now, we want to know which has the greatest percent by mass of oxygen. Well, you know how to calculate the percent by mass. It's simply, when you're given the formula, we just assume 1 mole, right? 1 mole of a compound. So what does 1 mole of the compound weigh? It has 2 times potassium, which is 39.10, plus 1 carbon, plus 3 oxygens. Well, we want percent by mass for oxygen, so the oxygen goes in the numerator also. Right? Times 100. All right? We'll calculate that one when we get the rest of them done. All right, for this one, we have 3 oxygens. In the numerator and the denominator. We have 1 nitrogen. And we have 1 hydrogen. Zinc oxide. We have 1 oxygen and 1 zinc, which is 6538 times 100. And then sulfur dioxide. We have 2 oxygens and also in the denominator, plus a sulfur, which is 28.09. Nope, sorry. 3207. My mistake. 32.07 times 100. And then the last one is 5 oxygens plus 2 phosphorus. 3097. There we go. Now our problem's set up. To make the comparison, all we have to do is calculate the values for each one. So I'm going to do, let's see, 48 and then 39.1, 2 times plus, and then 12.01 plus. And then, yep, and then divide times 100. So I get 34. Well, these numbers, molar masses, we can consider as exact numbers. So I'm going to just round it off to 2 places. 3473. Percent oxygen. Mass. All right. And then 14.01 and then 1.01 plus, and then divide. And this one is 7617. Okay, continuing on. And this is 19.66% oxygen. I'm just solving these expressions. 32 for oxygen, and then 32.07 added to that for the denominator, divide, and we get 49.95. And then finally, let's see, 30.97 or 2 times. And divide that, 35.19. Okay, there we have our calculated percent oxygen by mass. And to answer the question, greatest percent, just look at the numbers, and it's this one. Nitric acid has the highest percent of oxygen by mass. Okay? All right. Number 5 coming up. All right, compound X2Y is known to be. Here's this compound is made up of, well, if we just say atoms, 2 atoms of X and 1 atom of Y, but it could be polyatomic, we don't know. And we're also told that it's 60% by mass of X. 60% mass of X, right? And the question is, what's the percent Y by mass of the compound X2Y2? Okay. This sounds like a problem for Dalton's law of multiple proportions. So first of all, we have to know what's the percent by mass in this compound. So Y would be 40%, correct? Those are the only two elements in there, and 60% is X. The remaining of the 100% must be Y. Okay. Let's see, what's a good way to approach this one? If this one is held constant at 60%, well, what is 60% of? We can't say 60% over here because it's a different amount of Y. But if we say we have 100 grams, how about that? Say we have 100 grams of sample, then this would be 60 grams. It would also be 60 grams over here. And this would be 40 grams, right? But it would be twice as much over here. It would be 80 grams, right? So to answer the question, percent Y, and what I'm using here is Dalton's law of multiple proportions. Which says that if we hold this one constant, right, and then the combination of the next one, this would be twice as much. So we're going from 60 here to 40 to 80 here because it's twice as many. That's Dalton's law of multiple proportions. So now we can calculate the percent as 80 divided by, what's the total? 140, right? The total is 140. And I get 57% of Y mass. That's why the answer is D. But this is the governing law, Dalton's law of multiple proportions. Okay, next. We'll skip a few because they're repetitive. And take us down to 12, which is kind of repetitive itself, isn't it? That's all right. Practice, practice, practice. So the question is, what's the mass of calcium hydroxide if we have 5.826 moles of calcium hydroxide? Okay. And we want to go to mass, and the answers are in grams. Okay. So we need to convert to grams. Well, we know the conversion factor has to be moles on the bottom, grams on the top. Moles, moles. Moles cancel. So what's the value? We have to go to the periodic table. Calcium, 4008. Right? 2 oxygens, 2 hydrogens, and add them together. $74.10. There we go. Now all we have to do is crunch the numbers. 5.826. And I get, let's see, our values are in, well, it's a mixture. So we'll do scientific notation first. And that would be 4.317 times 10 to the squared. All right, we can keep 4 of these. So we can keep all of those, right? 4 significant figures. All right, that's not one of the answers. So we have to move this 2 places. See if that one's up there. Yep, that's A. All right. Number 13. Choose the pair of compounds with the same empirical formula. What do we mean by empirical formula? Definition. It's the simplest whole number ratio of atoms in a compound. Right? So if we have, all we have to do is compare these, A, B, C, D, and E. If we can take the one with the smallest numbers, multiply it by some whole number through the subscripts, and end up with the other compound, then we have a match, right? H2O cannot be made into H2O2, right? So A is false. How about B? C2H2 and C6H5. If we multiply C2H2 by 3, right? 3 times 2 is 6, and 3 times 2 is 6. We got a match. Okay? If we look at the others, you're going to find that you cannot convert one into the other by simple whole number multiplication. And if you don't have any squirrely ones like none of the above, one of the above, two of the above, only A or only B, those types of things, then once you find your answer, move on. Assuming you're getting the answer correctly, right? The thing about multiple choice questions is whoever creates them often looks at the possible ways that a student can make a mistake. And they take that mistake, it generates an incorrect answer, and they put that answer in as one of your options. All right, so if you do it wrong, you might see that answer and think it's right, but it's not. So you have to know what you're doing to choose the one that is the correct answer. And we have found the correct answer. That's B. All right, down to 15, 16, and 17. There we go on one page. 15. What's the molar mass of? Okay, it's like I'm going backwards. We already know how to do this. Barium hydroxide, right? So we have barium, which is a huge atom, 137.33. Right, grams per mole. And the rest of them, 2 oxygens, right? And 2 hydrogens. And let's see what that value comes out to. 137.33, and then 32, and then 2.02. Get 171.35 grams per mole, which would be A. That's fairly simple. And 16. Calculate the number of molecules in 0.000400 grams of gaseous oxygen. All right. So if we're starting off with, let's see, 0.000400 grams of gaseous oxygen. All right. In order to go from grams to numbers, we need a molar mass. What's the molar mass of oxygen? Well, you have to know that gaseous oxygen is diatomic. If you don't know that, then you can't get the right answer. The molar mass of this molecule is 32 grams per mole. Okay? That gives us moles. We want to know molecules. So we got rid of the grams. Now we're going to moles and molecules. All right? So that's 6.022 times 10 to the 23rd. And now we'll multiply them out. And we have how many significant figures in this number? These are not significant. These are significant. So it has 3 significant figures that has to be translated into the answer. Okay, 0.0004 and 32 divided, and then 6.022 times. So my calculator says 7.5275 times 10 to the 18th. We can only keep 3 of them. So it's 7.53 times 10 to the 18th molecules. Let's see. There it is. 7.53 times 10 to the 18th. All right, number 17. 22.6 grams of copper represents how many moles? So the question is moles. We're starting with 22.6 grams of copper. And if all we need to know is moles, this is a simple conversion. What's the molar mass of copper? We go to the periodic table because it's not given in the problem. 63.55. All right. I would estimate that as about 0.3 something. And we get 3 significant figures. So I come out with 3, 5, 5, 6, 2, 5, 5 moles. We can keep 3, 1, 2, 3. So that's 0.356 moles. Here we go. Scroll, scroll. Number 19. Calculate the number of moles of chlorine molecules in a sample that contains 7.380 times 10 to the 25th molecules of chlorine. All right, if we're looking at moles from molecules, doesn't matter if it's chlorine or not. We're already counting numbers, right? So chlorine is irrelevant. It's blue smoke. What we want to do is take 7.380 times 10 to the 25th. Molecules. And convert to moles. All right, molecules cancel, and the magic number is your favorite and mine, Avogadro's number. So we divide that number into this number. And I would say be in the neighborhood of 100, actually. 7.38025 and 6.022. 3 divide. Actually, it's 122.5506 moles. We can keep 4 of them. 1, 2, 3, 4. So 122.6 moles is our answer. All right, next, 22. Acetylene gas is 92.3% carbon, 7.7% hydrogen by mass, and its molar mass is 26 grams per mole. What's the molecular formula? All right. So that's basically what this whole chapter is about. Finding composition. Acetylene gas. So we know it has carbon and hydrogen only. All right. We're given 92.3% carbon. And the rest of it would be hydrogen. Right? And we're stuck because you can't convert percent into moles. Right? It's a dimensionless number. It simply means parts per 100 parts. Well, we're also told that it's mass. It's by mass. That is helpful, which means that it's 92.3 grams of carbon per 100 grams of the sample. And that's what we're going to do. We're going to say we have a 100-gram sample. Right? That means we have 92.3 grams of carbon and 7.7 grams of hydrogen. Now we can work with that. If we want to find out how many moles represented by that mass is the ratio of moles to moles in the formula. Okay? So we simply convert grams to moles. And this is carbon and hydrogen. There we go. So this gives us our first estimate of the mole ratio of carbon to hydrogen. 92.3 and 12.01. This is 7.69 moles of carbon, and 7.7 enter 1.01. Right, it's 7.62. All right. Now we come to the point where we need to get to a whole number. And normally what we would do is take the smallest one and divide it into both of them. But notice this one is so close to that one, that could be accounted for by experimental error. So we can essentially say that this is 1 to 1. That means the empirical formula is CH. And we want to know what multiplier of that one will yield 26 grams per mole. Well, now we go to this empirical formula, find out what the empirical weight is. That would be 12.01 and 1.01, which would be 13.02 grams per mole empirical weight. So this is going to increment by whole number values. If we make n equal 1, that's not 26. If we make it 2, then we get 26.04. That's it right there. So N equals 2. C2H2 is our formula, the molecular formula. All right. Pause for a second. I got a stubborn. There we go. That's what I get for carrying so much stuff in my pockets. All right, next one. 24. There it is. 24 says the molar mass of ammonium phosphate is. All right, here we are again with a named compound, and you can't answer the question until you can write the compound. What we have here is a compound that's composed of two polyatomic ions, ammonium, right, and phosphate. Just look them up in that table. So we need 3 of those. Remember, polyatomics, you can't change the subscripts. If you need more than one of them to balance charges, you have to use parentheses. Okay, so the molar mass then would be 3 times 14.01 for the nitrogens. 3 times 4 is 12 for the hydrogens. Oops, that's a 1. 1 phosphorus, which is 3097, and 4 oxygens. Right, and these are all grams per mole. So we can add apples and apples. And now it's just number crunching. 3 times that one. And then 12 times this one. Add that together, and then 30.97 and 64. So this answer is 149.12 grams per mole. All right, here's a case where that answer is not up there. So what do you do? Well, if you don't have any odd choices like none of the above, you pick the best answer. And the best answer is E, 149.09. There's a rounding error in there. That would explain why we're off by 0.03 of a gram per mole. Number 27. All right, 26.4 grams of nickel represents how many atoms? It's like we're going backwards. 26.4 grams of nickel, was it? Yeah. How many atoms is that? We have a chain conversion going on here. We need a bridge between mass and numbers, which is molar mass. Right? So nickel is 5869. Right? That gives us to moles. Atoms would be Avogadro's number. That's what's left. Six 0.022 times 10 to the 23rd. And now we just crunch the numbers. 58.69 divided, and then, okay. I messed up. I got to start over again. And then multiply. And I get, my calculator says 2.708823. times 10 to the 23rd atoms. We can keep 3 of them right there. 2.71 times 10 to the 23rd. Okay? If you've worked enough of these problems, you should be able to do these in your sleep. You know, and they'll be ready in the morning when you wake up. 31. All right, what's the mass of 8 atoms of copper in grams? We're looking for the mass. Okay? And we're starting with 8 atoms of copper. How do we get there? The only way you can get from numbers of something to mass is the molar mass. So we eventually need to be down here with a conversion factor that goes grams on the top and moles on the bottom. Right? And for copper, that would be 6355. Like that. Okay? I'm working the problem backwards. Now that we've got grams here, we need moles here that will cancel. So what's our ratio here? Well, atoms to moles is Avogadro's number. Right? Atoms cancel, leave us with moles. Then moles cancels and leaves us with grams. So now all we have to do is say 8 atoms divided by Avogadro's number times 63.55. And I get 8.44238 times 10 to the minus 22. This is a whole number, right? Remember, whole number, counting numbers are exact. So we can keep as many of those as we want. So what I would suggest is we go looking at the answers and we see that 8.44 times 10 to the minus 22, right? That's the available answer. So I picked that one. All right. Next, scroll. Skip repetitions. You'll notice that 42 is marked out. After I created the review document and wrote out all the hand-worked problems, I found that 42 was too much, right? We had not covered that subject yet. So rather than go back and rewrite all those answers, I just canceled 42. And now we go to 43. Now we are going to cover the topics that are related to number 42, but not in chapter 8. All right, 7.98 moles of sulfur trioxide molecules contain how many oxygen atoms? All right, we need to end up over here with oxygen atoms. And we're starting from 7.98 moles of sulfur trioxide. 7.98 moles of sulfur trioxide. Right? So we're going to numbers, and we have moles here. So the way you go from moles to numbers is Avogadro's number. Right? We have moles on the bottom. We can do molecules first. All right? Molecules first. And that gives us the numbers of sulfur trioxide molecules. Then we have a ratio. For every one of these, you have 3 oxygens. So we need to cancel the sulfur trioxides here, right? And leave us with oxygens. And the ratio is for every one of these, you have 3 of those. Okay. That's how we get to the answer. 7.98 and 6.022, 23rd, and then times 3. So I get, my calculator says 1441667 times 10 to the 25th oxygen atoms. This one has 3 significant figures in it, so we go there, 1.44 times 10 to the 23rd oxygen atoms. Okay. Oh, I misread my own number. That's 25. There we go. That's 43. And the next one I have marked is 49. All right. 4 molecules of chlorine weighs what? All right. The answers are in atomic mass units and grams. All right. So we have to account for either one. So which one do we want to do first? Well, let's see. We're starting with 4 molecules of chlorine. Chlorine is diatomic. Okay. So if we go to molecules, if we go to moles first, we can get grams. Okay. So if we go to moles first, molecules, moles, 6.022 times 10 to the 23rd. There. That'll give us moles. And then we can go to grams. For chlorine, that would be 35.45 times 2. And 9, 10, and 70.90. Okay. So let's see if grams is one of our answers. I made a mistake. Let me try that again. 4 enter 6.022 x 5 and 70.0 times. That would be, I'm going to go ahead and round. That's a counting number, so I can keep as many as I want. 71 times 10 to the minus 22 grams. All right. Is that one of the answers? No. The grams answers, that's not it. So we have to go to atomic mass units. So 4 molecules. How many atomic mass units are associated with chlorine? Well, for each chlorine, you have 35.45 atomic mass units for each chlorine. So times 2 is 70.90 atomic mass units. Right? Yep. And we have 4 of them. So 4 times that is 0, 6, and carry the 3, and then 4 times 7 is 280. So rounded off, it's 284 atomic mass units. That's C. Okay, so we had to work it 2 different ways. Now, if we'd been lucky, if we'd have started off trying to find atomic mass units first, then we would have got the right answer and we could just stop. All right. Next, 53. Which represents the greatest mass? All right. We got 1 mole each. This says they're all the same. If we have 1 mole of iron, we're just saying 1 mole of each one. We got iron, aluminum, rubidium, and titanium. Yes, titanium. So if we got 1 mole each and we're comparing mass, all we need to do is get the molar mass of each one from the periodic table. This is 5585. 5585 grams. Aluminum is 2698. Rubidium is 8547. And titanium is 4787. That's grams per mole. And it's easy to figure it out. Right? The answer is D. 1 mole of each one of these gives us those values. This is the greatest. Iron's the next. Titanium's the next. And aluminum is the lightest. That's why they use aluminum in airplanes, because it's so light. Now, sometimes, like for planes that are going to fly very high, very fast, you might have to use some titanium. And that's where the SR-71 came in. They used large amounts of titanium in that airplane because it was flying at Mach 3.2, 3.2 times the speed of sound at 85,000 feet. And it got really hot. Aluminum would melt at those temperatures, so they had to go to titanium, which is twice as heavy, almost twice as heavy. But it's actually stronger than aluminum, so they could use less of it. So the trade-off was you don't have to sacrifice weight because you can use less of it, and you get the resistance to heating that titanium offers. Let's see, what are we on? 61? Yeah, 61. A sample of metal weighing 2.59 grams is combined with oxygen. The metal oxide weighs 3.01 grams. The mass percent of oxygen in the compound is. All right. So let's see what we have. We're looking for the mass percent of oxygen. Right? That's what we're headed. That's the question. We're given 2.59 grams of a metal. 2.59 grams of some metal is combined with oxygen and yields something else. A metal oxide of 3.01 grams. 3.01 grams. That's the compound. Right? Some metal oxide. Okay. Now, how do we calculate percent? Well, 2.59 of that is the metal. That's the oxygen, right? We used up all the metal. Now it's over here, but it's combined with oxygen, which adds to its mass. And this is the amount that the oxygen added to its mass. So now we can calculate the percent oxygen. We just say 0.42 grams divided by the total times 100. And let's see, we have 3 significant figures. Well, actually, at this point, we only have 2, right? So I'm saying we have 14%. Yeah, 14% oxygen. We come in close. Yeah. E. Actually, E should be 14 without the zero. Right? That's claiming a significant figure that's not there because we did this calculation first to get that value, and now it's only got two significant figures. So it should be 14, not 14.0. The only other option you have is cannot be determined from the information given. Yes, it can. It's just that we claimed in the answer more significant figures than you're allowed. So the best answer is E. Okay. How about 62? Let's see. What's the molar mass of nitroglycerin? Whoa. One of my favorite molecules. Because it goes boom. C3H5, C3H5. And then the nitro part is NO3 3 times. Okay. Let's see. It's just asking for the molar mass. Okay. So 3 times 12.01 for the carbon, 5 times 1.01 for the hydrogen, 3 nitrogens, and 9 oxygens. All right. And if we do our math correctly, we should come up with 227 grams per mole. Okay. That's an interesting molecule. If we string the carbons together like that, and then we attach a nitrate to them, to each one, let's see, nitrate, nitrate, and then we have 5 hydrogens left. 1, 2, 3, 4. Ooh, I'm missing something. Because this says we need 1, 2, 3, 4. Oh, we do have 5. My mistake. There we go. So there's your nitroglycerin. And these bonds contain massive amounts of energy, and they're very, very unstable. It takes very little energy to start this molecule to break apart. And when we do, we start off with 4 moles of nitroglycerin, we end up with 29 moles of gases. So there's the explosive power of nitroglycerin. And that's for another day and another course, actually. All right, 63. A certain compound has an empirical formula of NH2O. NH2O. That's the empirical formula. Its molar mass is between 55 and 65. What's its molecular formula? All right, we're looking for that multiplier. So what's the empirical weight here? Well, we have 14.01, 2.02 for the hydrogens, and 16 for the oxygens. So that's 3, 0, 8, 12, and 3. This is grams per mole of that formula. Right? So all we have to do is say, if n equals 1, is that in the range of 55 to 65? If n equals 1, no, it doesn't give us that. If n equals 2, we get 64.06, right? That's it. So the formula is N2H4O2. 242. 64. The molar mass of blood sugar, that's just glucose, C6H12O6, also known as glucose. Sometimes they call it dextrose, but dextrose is more inclusive of other saccharides, other sugars. All right, you can have C6H12O6, and that could be fructose, which is a different structure. But glucose is definitely C6H12O6, and dextrose is substituted for it sometimes. So the molar mass of that one, all right, it's just 6 times 12.01. 12 times 1.01 for hydrogens, and 6 times 16. And if we do our math correctly, we should end up with 180.16 grams per mole. Okay, so it's a pretty sizable molecule. There are some that are a lot bigger, but it's no slouch, as they say. 67. All right, determine the percent composition by mass of lead in lead 2 fluoride. So this compound is named lead 2 fluoride, right? Because lead can be more than one charge, and we calculate the charge by this. 1 minus, 2 minuses, this must be a 2 plus. That's why it's that. Now, let's go ahead and answer the question. What's the percent composition by mass of lead? Right. We need the value for lead 207.21. 207.21 grams per mole. And then we also have it in the denominator. And plus, do it this way, plus 2 times fluorine, which is 19, to 2 decimal points, times 100. There we go. All right. So if we do our calculations correctly, we should end up with 84.5%. All right. And since these are all exact numbers, because they're molar masses, we can keep as many decimals as we want, and 3 is enough to answer the question. All right. Skip a few down to 75. Now, if we haven't covered a question that you're having problems with, then, and since there's nobody in face-to-face class and there's nobody zoomed in, then you'll have to get in touch with me by alternate means. If we haven't covered one and worked out a problem that is particularly troublesome to you. 75. Okay, calculate the number of moles of water molecules in 72 grams of water. All right. That's grams of water. We know that we want to end up with number of moles. So this is a single conversion factor. Why? Because we know how to go from grams to moles. This is 18.02 grams. So that would be about, that'd be about 4, in the neighborhood of 4, right? Best answer is 4.0, because the rest of them are nowhere near that. Okay. There you go. I estimated the answer and looked at the available ones and saw that the only one that came close to my estimate was E. So I saved myself the trouble of having to calculate. If I can do it in my head, at least to the degree of accuracy that's required to find the answer. 77. Determine the percent composition by mass of oxygen in Li2SO4. What is that? Lithium sulfate. Lithium sulfate. Right? Percent composition by mass of oxygen. We have 4 oxygens in the numerator and the denominator. Then we have sulfur, 3207. Right? Then we have 2 lithiums. Let's see, already got a plus. Lithium. What's lithium? Lithium is an alkali metal. It's over on the far right-hand side, and it's 6.94 times 100. Okay? That sets up the problem, and if we do our calculations correctly, we should end up with 58.21% by mass of oxygen. Okay? And we're down to 78. This is starting to get a little weak. See what else I got available here. This might work. 78. A compound is analyzed and found to contain 12.1% carbon, 16.2% oxygen, 71.7% chlorine by mass. What's the empirical formula? All right. 12.1% carbon. Okay. 16.2% oxygen. And chlorine is 71.7%. This is mass. Okay. We got the same problem as always. When we're confronted with percent, how do you get the grams so that you can convert these to moles and find the molar ratio of the atoms and elements in a compound? And we just assume 100 gram sample. Now we have 12.1%, excuse me, not percent, grams, 16.2 grams, and 71.7 grams. Okay, that looks suspicious to me. Yeah, empirical formula. Because 1 mole of carbon is 12.01. And oxygen is 16. And chlorine is 35.45 grams. All right. This is approximately 1. This is approximately 1. This is approximately 2. So I would say COCl2. Okay? Saved ourselves a lot of trouble by estimating the whole number ratios here. $83. All right, you have 12.6 grams of an unknown substance, A. Let's see, what's the question? What is the identity of A? All right, and it could be an element, it could be a compound, based on our answers. Right? 12.6 grams of A and 35 grams of chlorine gas. 12.6 grams of A. And how much chlorine? 35 grams of chlorine gas. All right. Substance A contains 1.5 times as many molecules as chlorine gas. So if we're combining A with chlorine, and we don't know what these ratios are, but we do know that A contains 1.5 times as many molecules as the chlorine gas. What is the identity of A? Okay, they're not reacting. My mistake. They're not reacting. We're just comparing them. Okay? So, how many moles is 35 grams of chlorine gas? Well, it's roughly 2 moles, right? Approximately 2 moles. And if A is 1.5 times as many molecules as chlorine gas, right? This would be 2 moles or 2 molecules for our comparison. This is 1.5 times that, so that'd be 3, right? 3 molecules, or yeah, 3 molecules. 1.5 times as many molecules. Okay, 3 molecules, or 3 moles. Okay. Well, if 3 moles is 12.6 grams per mole, 12.6 grams per 3 moles. Let's see if I'm barking up the wrong tree. 4.2, grams per mole. That doesn't help me. Yeah, I'm barking up the wrong tree. All right, starting over. Let's find out how many moles that actually is. Not just estimate. Let's actually calculate grams to moles. Right? Cl2 would be, okay, see, 35, 45 times 2, 0, 9, 79. And we'll find out how many moles that actually is. Zero 0.494 moles of chlorine gas. Okay. Now the problem says that A contains 1.5 times as many molecules. 1.5 times that times 1.5 is 0.7405 moles of A. So now we have grams per mole, 12.6 grams, and this is how many moles is represented by that. And that's 17.02 grams per mole. Okay, now we have the molar mass and we have some to select from. So we have A, B, C, D, and E. And our choices are uranium hexafluoride, oxygen, ammonia, and boron trifluoride, and carbon monoxide. We can estimate to get close to this and eliminate the rest of them. Uranium is 238. All right, so it can't be anywhere near that one. Oxygen is 32, right? 32 grams per mole. That can't be it. This is 14.01 plus 3.03 is 1704. That looks like a good choice. BF3 can't be it because this is 3 times 19, right? Which would be 2 and 3 is 57 just for the fluorines, right? That can't be it. And this is 12.01 plus 16.01, which is 28.02, right? That can't be it. So we found our answer. A is ammonia. 88. Calculate the percentage composition by mass of magnesium in this magnesium arsenate. Right. Magnesium arsenate, ASO4. ASO4. This is a 2 plus. This is a 3 minus. So we put a 3 over here and a 2 over there. Right? Okay. Percent by mass of magnesium. So we want in the numerator, we want 3 times magnesium. 2431. 2431. And also in the denominator. Right? Then we have 2 arsenics, which is arsenic. There it is, 7492. Okay. Then 8 oxygens. Right, times 100 equals what? Well, if we do our calculations correctly, we should end up with 20.8% by mass. Okay. And 91. We're getting close to the end of the highlighted ones. 91. Okay. A compound is composed of element X and hydrogen. Okay. So we have element X and hydrogen. Now, I don't know if hydrogen's on this side or on that side. I just put it there for now. If it's a hydride, it'll be on this side. If it's an acid, it'll be on the other side. Analysis shows that the compound is 80% by mass of X. 80% X. All right. With 3 times as many hydrogen atoms as X atoms. So we know that the subscript there is 3. Which element is element X? Okay. If this is 80% X, it has to be 20% hydrogen. Right? Okay. Let's say we have 100 grams of sample. That means we're talking about 20 grams of hydrogen. So we can say this many moles of hydrogen, 0.1 grams per mole. That'll get us to the number of moles of hydrogen in 100 grams. Nineteen point eight moles, excuse me, moles of hydrogen. Okay. So this value, this many moles, is a fourth of the total. Or if we divide by 3, that'll give us the number of moles of X, because the ratio is 3 to 1. So if we do like this, conversion factor, right? Moles of hydrogen, moles of hydrogen ratioed to the moles of X. This is 1 and this is 3, correct? We're converting moles of hydrogen to moles of X. Now, why do we want to do that? Because if we have a 100-gram sample, then X is 80 grams, right? 20 plus 80 is 100. If we can find out how many moles is represented, moles of X is represented by that 80 grams, we can calculate the molar mass. So we just divide 19.8 by 3. And 6.6. 6.6, right? Moles of X. So now that many moles gives us this many grams of X. 80 grams of X per 6.6 moles. So we take 80 and divide 6.6 in it, we got 12.12. 12.12 grams per mole. Now, we know of one way to determine, to find an element is the number of protons, right? The atomic number. We don't have the atomic number. Fortunately, the periodic table also goes from lower to higher relative to molar mass as well. So with very few exceptions, you can follow along and look for the closest one to 12.12 on the periodic table, and that would be carbon. Right? Carbon is 12.01. That's the closest one we can find. Right? So that's the element that we're looking for. X is carbon. Now, CH3, from my experience, I don't know of any compound that's CH3. Now, I know of some intermediates, like you can have a free radical here. That's possible, right, with an unpaired electron. But there's no stable compound that's CH3. But this is all academic anyway. 91. Now, you're not going to become comfortable with this type of reasoning unless you've worked a lot of these problems. I mean, if you're sitting back and just trying to memorize answers, then you're going to have a huge problem come exam time. 94. All right, you have 2 beakers on your lab table. Beaker 1 contains 32.07 grams of sulfur and beaker 2, 74.92 grams of arsenic. Which beaker contains the greatest number of atoms? Okay, so the question is comparing the number of atoms. Now, do we need to go all the way to atoms? No, we just need to go to a counting number. If we can get to moles without having to go all the way to atoms, then we can compare them, right? We get the right answer. 32.07 grams of sulfur. That's beaker 1. Beaker 2 has 74.92 grams of arsenic. Okay, and we're comparing the number of moles. Well, let's look at the molar mass. What's the molar mass for sulfur? Well, sulfur is 3207. 32.07 grams per mole. What does that mean? That means we have 1 mole of sulfur. How about arsenic? Arsenic is 7492. 74.92 grams per mole. That means we have 1 mole of arsenic, right? We have equal numbers. So beaker 2, wait a minute, 7492. Which beaker contains the greatest number of atoms? Yeah, beaker B. 1 and 2 contain the same number of atoms because there's 1 mole of each. That's true. That is the only true statement out of that bunch, is B. All right. 97. Convert 4.13 moles of phosphorus pentachloride to molecules. Okay. The conversion factor that we have to go to first is grams to moles. Right. That way, this moles will cancel, leave us with grams. What we need is the molar mass of that compound. 3097 for phosphorus, then 5 times 3545 for chlorine. Let's go ahead and do that. 30.97 and then 35.45 times 5. Add them together. 208.22. 208.22 times 4.13. And then we convert, wait a minute. Molecules. I'm making this harder than it needs to be. It doesn't matter that we have PCl5. You're probably wondering, where in the world am I going with this? If we only need the molecules, we only need 1 conversion factor. Right? 4.13 times 6.022 exponent 23 times. And this, 3 significant figures, is 2.49 times 10 to the 24th molecules. And PCl5 is irrelevant. Once you've already gone to numbers, you don't need to know that it's phosphorus pentachloride. The answer is 2.49 times 10 to the 24th, no matter what the molecule is. 99. Five 5.392 grams of hydrogen gas contains what? Atoms of hydrogen, molecules of hydrogen, atoms of oxygen. If you've got 5.392 grams of hydrogen, where'd the oxygen come from? Right, this is not a nuclear reaction. 5.392 grams of hydrogen. That's where we're starting. Hydrogen gas, H2. So, if we've got that many grams of hydrogen, 5 atoms of hydrogen is not going to give you that one. A, B, C, D, and E. So we can eliminate some of them already. A is impossible. That'll never work. 12 atoms of oxygen is just ridiculous. So we can take a closer look at B, C, and D and say, okay, B and C are hydrogen molecules, right? B is in terms of molecules, C is in terms of moles, and D is in terms of atoms. So let's start with what we have. This many grams gives us what? How many moles? Let's see what that does. Maybe that's the right answer. If we're looking for moles of hydrogen gas, that's one of the answers, C. So let's see. It's 1 mole, and hydrogen would be 2.02 grams because there are 2 of them. That's 2.67. 669 moles of H2. All right. So C is wrong. Can't be. So what else do we have? Hydrogen molecules. If that's the moles, we can convert that to molecules. All we need is Avogadro's number again. Molecule. 6.022 times 10 to the 23rd. Okay. 6.022 3 times. This is 1.607 times 10 to the 24th molecules of hydrogen. Okay. Hydrogen molecules is C. Oh, we already did that one. B, 3.22 hydrogen molecules. No, it's 1.607. So B is wrong also. Process of elimination, D should be the answer. So let's confirm it. If this is the number of molecules, how many atoms is that? We need a conversion factor. I'm going to go this direction. That'll take molecules of H2 and atoms of H. And the ratio is 2 to 1, right? 2 atoms for every molecule. So 2 times that is 3.21 times 10 to the 24th atoms. Right? And the closest answer to that one is D. That's why D is the answer. Okay. Number 100. Consider equal mole samples of dinitrogen monoxide, aluminum nitrate, and potassium cyanide. Rank these from least to greatest number of nitrogen atoms in each sample. All right. So, greatest to least number of nitrogen atoms in each sample. If we have equal mole samples, we can pick it, right? 1 mole, 2 moles, 3 moles. Let's just pick 1 mole. It makes it a whole lot easier. 1 mole of dinitrogen monoxide. Right? 1 mole of that. Aluminum nitrate. Right? This is 3 plus. That's 1 minus. So we need that formula. And potassium cyanide. Like that. Okay. Back to the question. Rank least to greatest number of nitrogen atoms. If we have 1 mole of each, right? If we have 1 mole of N2O, then the ratio is N N2O to nitrogen is 2 of these for every 1 of those. So that means we have 2 moles of nitrogen. In this case, if we have 1 mole of that, we have 3 moles of nitrogen. Right? 3 times 1 is 3. Out of 1 mole of that formula, we have 3 moles of nitrogen. And out of 1 mole of this, we have 1 mole of nitrogen. So if we rank them from least to greatest, we're going to say this one is first, this one is second, this one is third. So potassium cyanide is either A or E. The second one would be N2O, which is E. Right? E is the best answer. All right. 101. Calculate the mass of 3.53 times 10 to the 26 atoms of silver. Right? Yep. And we want the mass. We want to end up with mass. So we know that we have to have a conversion factor down here that gives us grams. And the ratio that we know is molar mass. Okay. So silver is 107.87. Right, that'll give us grams. We need something that'll cancel moles. Right? And how many atoms of silver are there in a mole? 6.022 times 10 to the 23rd in 1 mole. Moles cancel, atoms cancel. Now we just crunch the numbers. 3.53 exponent 26 and 6.022 exponent 3 and 107.87 times. Whoa. Did I do that right? 6.33. Yeah. That's a lot of silver. I wouldn't mind having that in my bank account. So 3 significant figures. I'm going to go ahead and round to 6.32 times 10 to the 4th grams. Yeah, let's see. Now, if the answer were in kilograms, how would we deal with that? Right? 6.32 times 10 to the 4th grams is the same thing as 6.32 times 10 to the 1st times 10 to the 3rd grams, right? I just factored 10 to the 3rd out of their number and put it over here. 10 to the 3rd is kilo. So this would be kilograms. And this would be 63.2 kilograms. Okay? If I got sneaky and put kilograms in there along with the grams, and this was the answer, then you'd be able to figure it out. 106. Oh yeah, we're doing okay. We're getting close to the end of the highlighted ones. 106. The mass in grams of 3.52 moles of nitrogen gas. All right, here's another problem where, well, actually, we tell you what the nitrogen gas is. That was nice, wasn't it? 3.52 moles of N2. And we want to find out how many grams that is, right? Look at the answers. The mass in grams. They're all in grams. So we know that we can get rid of moles and leave us with grams. What's the molar mass of nitrogen? 2 times 14.01, right? 28.02. Two times, and I get 98.6. That one of our answers? Yep, sure is. That's 106. All right. We have any more? 110. How we doing? We still got a few. Let's do 110. Calculate the molecular formula of a compound with an empirical formula of CH2O and a molar mass of 180 grams per mole. If the empirical formula is CH2O, right, we need something there that will give us 180 grams per mole. Right. So the empirical weight of this one is 12.01, 2.02, 16. 12.01, and 16. This is 30.03. So if that's equal to 1, there's no way. 2 is only 60. Right? 3 would be around 90. 4 would be around 120. 5 would be about 150. And 6 would be 180. So this N is equal to 6, and we have C6H12O6. Glucose or dextrose. $113. $113. There we go. 60.2 milliliter sample of mercury with this density contains how many atoms of mercury? Right. This is a dimensional analysis problem. We want to end up with atoms of mercury. And we're starting with 60.2 milliliters of mercury. We're not going to get to numbers until we can change to moles. Right? So we've got to change this to some mass value. Get rid of milliliters, leave us with grams. Fortunately, we have just a ticket, 13.6 grams per milliliter. Okay? That gives us grams. Now we can convert grams to moles. Right? What's the molar mass of mercury? Well, let's see. 200.59. Right? There we go. Now we can convert moles to atoms. There we go. Now that's the hard part. The rest is just putting the numbers in and hitting the buttons. And I get 4, 5, 7, 9. 5 times 10 to the 24th. Right. Chop it off at 3. 2.46 times 10 to the 24th atoms of mercury. A. All right. Let's see. Got any more? Ooh, we do have 16. 116. We have 10 minutes. Vinegar contains carbon, hydrogen, oxygen with percent mass of carbon and hydrogen. It doesn't give us oxygen. Why not? Because of the method of analysis. We combusted vinegar in an oxygen atmosphere, so we can't do a direct calculation of oxygen. If we know it only has carbon, hydrogen, and oxygen in it, and we know carbon and hydrogen, subtract them from 100 and you get your oxygen. If the molar mass of vinegar is 60 grams per mole, what's its molecular formula? All right. So start off with carbon at 40.01%. Hydrogen is 6.70%. So oxygen would be 40.01, and 6.7 plus is 46.7, and subtract that from 100. 53.3. And 53.29. And that should add up to 100%. Okay, now we know how to do this. Assume a 100-gram sample. This will be 40.01 grams of carbon, 6.70 grams of hydrogen, and 53.29 grams of oxygen. Now we can convert. Henry Ford time. Grams, 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 moles, moles, and moles. Magic number for oxygen, 16 grams per mole. Hydrogen, 1.01 grams per mole. Carbon, 12.01 grams per mole. Okay, so let's find out what their molar ratios are. See, I've already got that one in there, so let me do the bottom one first. This is 3.33. .7 divided by 1.01 is 6.63. And carbon is 40.01 divided by 12.01. And that's 3.33. All right. These are the same. So if we divide through by 3.33, right? 3.33, 3.33, and 3.33. These are both 1. What's that? 6.63 divided by 3.33. Close enough. That's 2. Okay. So we know the empirical formula is CH2O. We just need a multiplier. So the empirical weight is 12.01 plus 2.02 for the hydrogen plus 16 for the oxygen. This is 30.03, and the molecular weight is 60. Right? So 60 divided by 3.03 is approximately 2. That's equal to N. So we have C2H4O2. C2H4O2. Now that's one way to write it. Another way to write it is put the hydrogen out front. That's the acidic hydrogen. Then you have C2H3O2. With this is the acetate ion, and that's plus. So put it in solution, that first proton goes out into water. Well, not all of them, but some of them. Another way to write it, and you may see this some places, is this way. Right? That represents a linear expression of the formula, of the structure. So it would be like this. Right? Those 3 hydrogens bound to that carbon, then we would have an oxygen, and hydrogen. Like that. That's what's meant by that formula. And this right here, that's the acidic hydrogen. That's the one that leaves the molecule to make your solution acidic and make your vinegar sour. Okay, 116, is that the last one? That was the last one. Okay. But to answer the question, that's all you need. All right. If you have any questions, you know how to get in touch with me. Check out my schedule and contacts in Brightspace and in the syllabus. And that's it. So next time you see this material will be on the exam, which it will be next Tuesday. Let's see, this is the 19th, 24th. 24th of February will be the deadline for this exam. Midnight on the 24th. And we're done.